of electron. So, if I consider a normal hydrogen like atom, so in this particular case the electron is revolving. So, we are now concerned about what its energy is. So, now let us understand what type of energies will that electron possess. So, first of all, because this electron is moving in a circle with some speed, it has kinetic energy, and apart from that, because of the interaction with the positive charge at the center, the nucleus, we can say that this system also possesses some potential energy, and we already know how to find the potential energy of a two charge system. So, it possesses both the energies. So, the total energy will be the sum of these two energies. So, I will first write the energies individually. So, I can write kinetic energy of that electron as half mv square, and to understand this half mv square, we have already written this expression from Bohr's first postulate, which is kZe into E divided by r square is equal to mv square by r. Force is equal to the centripetal force. I mean, the Coulombic force of attraction is providing the centripetal force. So, now to find kinetic energy, I need the term mv square or half mv square, and I have that over here. So, what I will do is I will cancel out r on either side. So, I have mv square is equal to k Ze square by r. I need half mv square. So, I can write kinetic energy of the electron as half of k times Ze square by r. So, which is kZe square by 2r. Okay. So, now we have found the kinetic energy of the electron. So, now in the similar way, let us also calculate the potential energy of the electron. So, we can write potential energy of the electron or this system, the interaction energy, as k q1 q2 by r. So, I will just use that k. q1 is Ze, a positive charge, q2 is minus E, so minus E divided by r, and this value comes as minus kZe square by r. So, now when you look at this, so kinetic energy is kZe square by 2r and potential energy is minus kZe square by r, and if I have to find the total energy of this system, I can write total energy of that electron as kinetic energy plus potential energy, and when I add those two terms, I will be getting minus kZe square by 2r. So, we have all the three energies here. This can also be called as the mechanical energy of the system. So, now let us write a relation between these three. So, we can easily see that kinetic energy is just the negative of total energy and potential energy is just double of this particular value. So, I can write it like this. So, total energy, I will represent it with T. So, I can write total energy is equal to potential energy by 2, right. So, it is potential energy by 2, and it is also equal to, we can write this expression as negative of kinetic energy. The magnitude of these two are same, total energy is just negative. So, I can write this as kinetic energy by minus of K. So, it is minus of K. So, that would be the expression for energy of an electron. So, now that we have defined energies and all types of energies, let us see how these energies vary with different orbits and different atoms. So, total energy of an electron in an orbit can be written by this expression. So, to find the energy in the nth orbit, what I will do here is I will just substitute the value of r as the radius of nth orbit. We already have the expression which we derived earlier. So, I can write total energy Te is equal to minus kZe square by 2 times the value of r is n square h square by 4 pi square m e square z into k. So, this is the value of Rn to be specific. So, when I rearrange the terms, I will be getting the total energy as, so you can just see there, it turns out to be 2 and 2 gets cancelled, and you would be getting 2 pi square m e power 4 z square k square divided by n square h square. So, that is the expression which we get. You just rearrange the terms, you do all these derivations on your own, you can easily do it by yourself. So, now here if I separate out all the constants and bring z and n separately, I would be getting a constant, or there is a negative sign. So, there is a negative sign. So, I will get a constant, and in the numerator I have z square, in the denominator I have n square. So, z square by n square. And if you evaluate that constant by substituting each and every value, so actually you will get everything once you evaluate everything by substituting the SI units, you will get the value here in joules. But as I told you earlier, throughout atomic physics we will be representing the energies in electron volts. That is more useful for us. So, when I write this expression, when I convert that into electron volts by using this conversion factor, 1 electron volt is equal to 1.6 into 10 power minus 19 joules. So, by using this conversion factor, when I convert this expression into electron volts, the value which I get here is 13.6 electron volts. So, that would be the energy of an electron in a hydrogen like atom in its nth orbit. So, minus 13.6 electron volts into z square by n square. Okay. So, that is the expression. So, now let us understand how these energy levels are. I mean, what would be the energy level of the electron in different orbits of hydrogen, atomic hydrogen. So, let us see that. So, I will be using a representation here, maybe you are all aware of that also already. I will be representing each energy level with different steps, showing the difference in energy levels and all that. So, first let me calculate few energy levels by using this. I am doing the energy level diagram. So, what I am drawing here is an energy level diagram for hydrogen. Okay. First let me calculate few values of energy. So, Z is 1 for hydrogen, and first I will find out the energy of the electron in the first orbit. So, energy of electron in first orbit is nothing but, so this is 1 and this is 1. So, it comes out to be minus 13.6 electron volt. Now, similarly, energy of second orbit is minus 13.6 into, so this is 1 and this is 2 for the second orbit. So, 1 by 4, and this value comes around as minus 3.4 electron volt. And similarly, if I calculate energy of third orbit, so the value of that would be minus 13.6 by 9, and it is approximately minus 1.51 electron volts. And similarly, energy of fourth orbit would be minus 13.6 by 16, and the value of that would be minus 0.85 electron volts, and so on. So, for now let us understand up to here, and let us see what these energy levels suggest, how what idea that do they give us about how the energy levels are present. So, what I will do is I will represent this first energy level for the electron in its first orbit. We can also call it as ground state. So, I will represent this energy level first. So, let us consider that this is the ground state. So, this level here corresponds to minus 13.6 electron volts. Okay, so this also corresponds to n is equal to 1. Now, similarly, so what I am doing here is by representing this as minus 13.6, I am also, let us say, considering that this value here is my reference, which corresponds to an energy of 0. and all the levels which are below 0 corresponds to negative energies. So, taking this as my reference, I am just representing all these values on the energy level diagram. So, the first orbit has 13.6 electron volts below the 0 level. So, that is how you should understand it. Okay. Now, let us represent the energy level of the second orbit. The value of that came around as minus 3.4 electron volts. So, minus 3.4 would be closer to 0 than minus 13.6. So, it would be somewhere over here. So, this is where the second energy level would be. So, this corresponds to n is equal to 2 and the value of this is minus 3.4 electron volt. Now, similarly, third energy level is minus 1.51. So, on the energy diagram it would be somewhere over here. So, this corresponds to n is equal to 3 and the value of energy here is minus 1.51 electron volt. And similarly, fourth energy level is minus 0.85. So, that would be somewhere over here. So, this corresponds to n is equal to 4 and the energy is minus 0.85 electron volt. And similarly, we can draw many such energy levels, and so you can basically understand that the energy levels would be like this as we go ahead. So, now you can actually see a pattern over here. So, as I go to higher and higher energy levels, we can observe that the difference in energy level from this state to the next possible state is decreasing continuously. So, you can actually observe that the energy level difference between these two is minus 13.6 electron volts, or you can say this is the higher energy level. So, this energy minus this energy, when I find the difference between these two energies, the value comes out as 10.2 electron volt. So, second energy level is 10.2 electron volts higher than the first energy level. Now, similarly, the energy difference between these two, you can calculate that. So, just subtract this value from this value, minus 1.51 minus 3.4. It is basically 3.4 minus 1.51. So, what would be the value of that? 3, 10, 9, 8 and 1. So, it is approximately 1.89. I can take it as 1.9 electron volt. So, you can basically understand, you get the idea that as I go higher and higher, the energy level, the difference in energy levels with the next successive state is decreasing. So, that is how the energy levels would be, and the higher I go, the energy levels will tend to 0. And when does it actually become 0? Which energy level has an energy of 0? It is infinity. So, basically what that means is that electron which is taken far away from the nucleus, which has no way to interact with this nucleus, will have an energy of 0. So, they can actually ask you a question like this: how much is the energy required? So, for example, if you have a nucleus and you have an electron, and let us say this is in n is equal to 1 state, the ground state, we call it as ground state. So, they can ask a question like this: what is the energy that should be supplied to this electron to remove it from the nucleus, to remove it from the atom, to send it to infinity? So, whenever they ask you something like that, to remove the electron, whenever they are asking you to completely remove the electron, they mean to say that you need to make the electron transition from n is equal to 1 to n is equal to infinity. So, n is equal to infinity basically corresponds to complete detachment from the atom. So, that is what it means. So, can you tell me how much is the energy required to remove the electron from ground state of a hydrogen atom? It means that, so an electron which is in this energy level should be taken to this energy level, so to 0. You know that at 0 we already have seen this expression. When the electron is at infinity, we can say that the potential energy becomes 0, and as potential energy becomes 0, and because it is so far away, the speed of the electron will also be very less. So, as a result, kinetic energy becomes 0 and total energy also becomes 0, or you can just understand that as r tends to infinity, this value tends to 0. So removing an electron basically means taking the electron from n is equal to 1 to n is equal to infinity. So what was the answer for what I asked just earlier? How much energy should be given to this electron to remove it from the nucleus, to remove it from the atom? So the answer for that would be 13.6 electron volts. So when I give 13.6 electron volts to this electron, it goes from an energy state of minus 13.6 electron volts to 0. So which means it gets completely detached from the atom. So what if it is given an energy which is less than that value? For example, let us say if it is given 10.2 electron volts. So if this electron is given 10.2 electron volts, it excites to the next energy level. The energy difference between this level and this level is 10.2 electron volts. So taking that 10.2 electron volts, the electron from here goes to this state. Now if you see here, see, knowing these values will be very important to you. It is better you memorize these values, because it saves a lot of time during whether you are solving any numericals or in exam. So you can easily identify what states they are asking you about by just looking at the numbers. So it is very much important for you to know each and every one of these values by heart. Okay, so not just the energy levels, even the difference in energy levels, and also the energy differences between nth orbit and first orbit. What I mean to say is, so the energy difference between 1 and 2 is 10.2 electron volts. The energy difference between 1 and 3, so you can just see that. What is the energy difference between third orbit and first orbit? It is nothing but minus 1.51 minus 13.6 electron volts, and the value comes out to be some 12.1 electron volt. So these values are very important for us. You need to know those values. So because whenever you have a question wherein they give you that electron is in the ground state and it is supplied with an energy of 12.1 electron volts, so you just can't keep solving the use the information for solving and do all that. You can directly understand by looking at the 12.1 electron volts that the electron has transitioned from n is equal to 1 to n is equal to 3. So that is what I mean. It saves a lot of time. So it is better you know these values. And similarly, what is the difference between first state and fourth state? So you just subtract this value, or subtract minus 13.6 from minus 0.85. So you can do that. So you will be getting 13.6 minus 0.85, and what would be the value of that approximately? So 15. So that would be nearly 5, 15. So 12.75 electron volts will be the difference. So the difference between this state and this state is 12.75 electron volts. So I would suggest you know these values for sure, energies of each and every level in hydrogen, at least till fourth level. And similarly, I would also suggest you remember the values of energy difference between 1, 2, 1, 3 and 1, 4. So these values should be very clear to you. Okay. After this, let's talk about the excitation and de-excitation of electrons in hydrogen. Okay, students. So excitation and de-excitation. So what it basically means is, so excitation is a process where you are giving energy to the electron and taking that electron from a lower energy state to a higher energy state. So if, for example, if here you can see that this is the first orbit, the electron is in the first orbit. So now when you supply energy to that electron, so that electron takes the energy and it might go to second orbit or to third orbit or to fourth orbit. So going to higher orbits is what we call as excitation, and de-excitation is just the opposite. If for example, if there is an electron in a higher orbit, so let us say it is in fourth orbit, so that electron losing its energy and coming back either to the third state or to the second state or to the first state, so that process is what we call as de-excitation. So it is pretty simple. So now let us analyze what happens during excitations and de-excitations. So, let us first consider that the electron is in the ground state, and so excitation of this electron can be done generally in two ways. One is by supplying it the energy using a photon by using light. So, whenever light goes and strikes the electron, so the energy of the photon gets transferred to the electron, and the electron can use that energy to transition to higher energy states. And the other way in which you can make the electron transition is by colliding it with more electrons. So, if there is another electron which is going and striking it, or any other particle which goes and strikes that electron, so during that collision the energy, kinetic energy, will get transferred from that particle which is going and striking it, and the electron takes that kinetic energy and it just uses that to transition from a lower state to a higher state. So, generally excitations can occur in these two ways. One is through photons, and the second one is through collisions. So, these are the ways in which excitation can be done. So, we will first learn about how excitations can be done using photons. Excitation through collisions, we will discuss it at the end of this topic. So, let us see how to excite an electron using a photon. So, now you all know the energy levels basically, I have already drawn them here. So, electron in the first orbit has an energy of minus 13.6 electron volt, and let us say I need to make this electron transition from first orbit to second orbit. So, you all know by now that to make the electron go from here to here, I need to give this much of energy difference, and the energy difference between first and second state is 10.2 electron volts. Now, it means that this electron, if it is incident with light which has photons having an energy of 10.2 electron volts, it absorbs the 10.2 electron volt photon and it moves from this state to this state. Okay, it is pretty straightforward, but there is one very important thing which you will have to be aware of in this particular case. What happens if this electron, or the energy or the light which is incident on this atom, has photons having an energy which is less than 10.2 electron volts. Let us say it has an energy of some 9.5 electron volts. So, this photon has an energy of 9.5 electron volts. So, all the photons in this beam have an energy of 9.5 electron volts. So, what happens if such a photon goes and strikes the electron? Can you guess what might happen? So, here what happens is that this electron will not absorb this photon, because this electron needs a minimum of 10.2 electron volts to get released from this state and move to some other state. The minimum energy that it requires is 10.2, and all the other transitions require more energy to move from 1 to 3 or 1 to 4 or 1 to 5. So, all those energy differences are greater than the energy difference from 1 to 2. So, the minimum energy which it requires to leave this first orbit is 10.2 electron volts, and if your photon is not sufficient, it has no energy, it has no sufficient energy to make this electron transition, in such a scenario the electron will not absorb that photon. So, in that case what happens is that this photon strikes the electron and just reflects back. So, there is no absorption going to happen there, there is no transfer of energy to the electron. It is not even possible that the electron can absorb the photon, go to some other halfway, go from somewhere between 1 to second state and then come back from there. So, nothing like that also happens, because electron can only exist in this state or in this state. There is no moving from here to here, there is no path, there is no movement from 1 to 2. So, nothing like that exists here. So, if the energy is sufficient, if the energy given by the photon is 10.2, the electron vanishes from here, it suddenly disappears from here and it suddenly pops up in the second orbit. If the energy is not sufficient, the photon strikes the electron and just gets reflected back. There is no absorption going to happen. I have already told you in photoelectric effect that the interaction between a photon and an electron is like an all in or nothing. So, this photon can give all of this 9.5 electron volts to this electron or give nothing to that electron. There is no halfway, there is no giving the electron 9 electron volts and taking 0.5 electron volts back with the photon. So, nothing like that is going to happen. The photon either gives the energy completely or gives no energy at all, and in this case it does not give the energy completely because the electron can't utilize that energy. So, not just in this case, even if let us say the photon has an energy of 11 electron volts, let us just consider a scenario like this. So, if the energy of the photon is 11 electron volts, so can you guess what might happen in this scenario? A photon having 11 electron volts, if it strikes the electron, so what is going to happen? You know that electron needs 10.2 electron volts to go from 1 to 2, and obviously this 11 electron volts of energy is not sufficient for this electron to go from 1 to 3, because to go from 1 to 3, we have earlier discussed that the energy required is 12.1 electron volt. So, this 11 is somewhere in between these two. So, what do you think might happen in this scenario? Is it possible that out of this 11 electron volt, this electron takes 10.2 electron volts and give the photon the remaining 0.8 electron volts? Is it possible? Is it possible that this photon, after striking the electron gets excited to this state and the remaining 0.8 energy or 0.8 electron volt of energy will once again go away in the form of a photon? Is that possible? The answer is no, and the reason is I have told you earlier, this photon can either give its energy completely or give no energy at all, and in this case its complete energy cannot be utilized by the electron. So, the electron will not take that energy at all. So, even if the energy is more than 10.2, because electron can't utilize that energy completely, the electron takes no energy from the photon, and this photon after striking the electron gets reflected back. So, the most important point which we will have to understand here is that electron can only take energies which are equal to the difference in these energy levels. Only that photons can be absorbed by the electron. It cannot absorb any photon which is incident on it. So, that is a very, very important point in understanding the later parts of the later concepts which we are going to deal with. I will just write down a few points over here. An electron in ground state if incident with photons. So, I will just write down a list of few photons over here having different energies. So, I want you to identify which of those photons can be absorbed by the electron which is in the ground state. So, let us say the first photon has an energy of 5 electron volts, second photon has an energy of 10.2 electron volts, and third photon has an energy of 11 electron volts, and fourth 12 or 12.1 let us say, and the next one let us say is some 13 electron volts, and the next one is 13.6 electron volts. So, let us consider these 6 cases and see if these different types of photons are incident onto an atom with electron in its ground state, which of these photons may be absorbed. Okay. So, I guess you must have already known the answers for this. So, 5 electron volts cannot be completely utilized by the electron. So, this will not get absorbed, and 10.2 electron volts can be completely absorbed by the electron to transition into the second state. So, this can be absorbed by the electron, and 11 electron volts cannot be completely absorbed because there is no energy difference corresponding to 11. After 10.2, electron needs only 12.1, it can't have any energy between these two. So, even this cannot be absorbed, and similarly 12.1 is the energy difference between 1 and 3. So, this can be absorbed, and 13 electron volts Actually, you need to know few more values to see whether 13 electron volts lies does this value correspond to any energy difference between two states. As of now, we can't tell just by looking at that number. So, let us just leave this value for now. If you want, you can calculate and try. You can check whether there is any energy difference, and if there is any level corresponding to an energy difference of 13 electron volts. And 13.6 electron volts can be absorbed because 13.6 is the energy difference between ground state and infinity, where the electron is completely removed from the atom. So, these are the photons which can be absorbed, whereas these cannot be absorbed. So, that is how we can understand the excitation of an atom or an electron using photon. And we can also talk about few more energy states, energies of photons. It might also be possible that the photon which is incident might have an energy greater than 13.6 electron volts. So, if for example, if there is another photon, let us say a photon with an energy of, let us say, some 20 electron volts is incident. Okay, can you guess what might happen in this case? So, because the energy which we are giving through photon in this case is greater than 13.6. So, 13.6 is the energy required to reach this n is equal to infinity state. So, do not think that it can only utilize 13.6 energy and not more than that, because once it absorbs 13.6 electron volts of energy, the electron is out of the bounds of the atom. It means that the atom no more controls that electron. That electron can have any energy which it can have, which is possible once it goes away from the atom. See, I'll explain this again, please concentrate. What I am saying here is that as long as the electron is bound to the atom, as long as the electron has not gone away from the bounds, this electron can only have specific energy levels. After this energy, the electron can only have this energy. After this, it can only have this energy. After this, it can only have this energy, because all these energy levels are dictated by the nucleus, the interaction with the nucleus. So, that is what decides the energy. But once the electron has crossed this level and gone out, it means that it has no interaction with the nucleus anymore, and it can have any kind of energy which is given to it. So, that means that whenever 20 electron volts of energy is given to the electron in ground state, so it uses 13.6 electron volts of energy to go to infinity, and once it goes to infinity, it is no longer controlled by the nucleus. So, the remaining energy will appear in the form of its kinetic energy of the electron. So, in this case, we can say that electron is removed from atom, and as I told you, once it is removed from the atom, the electron can have any kind of energy. There is no limitation on the electron to have only specific energy level. So, once it is removed from the atom, the remaining energy which is left, and the remaining energy which is left is 20 minus 13.6. So, this appears as kinetic energy of the electron. So, this is what you will have to know here. So, as long as the electron is within different orbits, it can only have specific energies and it can only absorb specific energies, but once you are giving an energy which is sufficient enough to remove the electron altogether, and any energy greater than that can be absorbed by the electron. So, this is how we understand excitation of an electron, and keep in mind that this first state is basically called as the ground state, and this n is equal to 2 state is basically called as the first excited state. So, first one excitation, the smallest excitation that can happen is 1 to 2. So, second state or n is equal to 2 state is also called as first excited state, and n is equal to 3 state is called as second excited state, and n is equal to 4 corresponds to third excited state, and so on. So you can generalize this and say that nth state basically means n minus 1th excited state. So both are one and the same. Nth state and n minus 1th excited state both mean the same. Okay, so that is about excitation. So let's discuss about de-excitation now. So I've told you earlier that de-excitation basically means an electron which is in the higher energy level loses some of the energy and transitions to lower energy level, and when such a thing happens, the difference in that energy levels will be released in the form of a photon. And one important thing you'll have to keep in mind, I've told this during the third postulate, that the difference in energies is released only in the form of a single photon. You can't say that whenever an electron transitions, let's say from second state to ground state, the difference of 10.2 electron volts can't be released as 2 photons of 5.1 each, or there is no concept of emission of 2 photons for one transition. One transition corresponds to 1 photon only. So this is something which should be very clear to you. So let us just consider a scenario where this electron is initially in a state N2 and it transitions to a lower energy level, some N1. So I'm just taking general values. So from N2 state to N1 state. So now third postulate of Bohr states that the difference in these two energies will be released in the form of a photon. So we can say that initial energy EI minus final energy EF is equal to hc by lambda. So let us do the derivation here for a general hydrogen like atom, so Ze, which has an atomic number of Z. So what is the energy of an electron in n2th orbit of an atom having atomic number Z? So we already know that it can be written as minus 13.6 into Z square by n2 square minus of the final energy, because it is coming to n1th state, so we can write it as 13.6 into Z square by n1 square. So this is equal to hc by lambda. So now let us find the value of lambda, or what I'll do is I'll just send this hc to the other side and I'll write this expression once again. So if you see here, this becomes plus, minus of minus becomes plus, and I can write 1 by lambda is equal to I should send this hc to this side. So I would be getting 13.6 Z square by hc, and if I simplify it further, I'll get 1 by n1 square minus 1 by n2 square. So that is the expression which we would be getting here. So 1 by lambda, the inverse of wavelength. So it is also called wave number, which we'll learn about that later. So 1 by lambda is equal to 13.6 Z square by hc into 1 by n1 square minus 1 by n2 square. So that is the expression which we would be getting. So this 13.6 here is in electron volts. So this value is in electron volts, and you already know the value of hc. So I can also substitute the value of hc in electron volts. Okay, I'll write that in the next step. So 1 by lambda is equal to, this is nothing but 13.6 electron volt into Z square by, so we discussed this earlier, hc value can be written as 1240 electron volt nanometer. So I can write this as 1240 electron volt nanometer into 1 by n1 square minus 1 by n2 square. So simplifying this by electron volt and electron volt gets cancelled, and when you simplify this, this value turns out to be 1 by lambda is equal to So nanometer, when it goes to the numerator, it becomes 10 power 9, and simplifying this will give you 10967800 meter inverse into 1 by n1 square minus 1 by n2 square into z square. So this constant term which we got here, we call it as Rydberg's constant. It is denoted with capital R. So I will replace this with capital R and I will rewrite this expression once again. So the final expression which I would be getting is 1 by lambda is equal to rz square into 1 by n1 square minus 1 by n2 square. So where the value of r is 10967800 meter inverse, or if you want to write it in approximately, you can write it as 1.1 into 10 power 7 meter inverse. So that is how we can find out the wavelength of the photon which is emitted when an electron de-excites from a higher energy level to a lower energy level. So it is not that this is only used for de-excitation. You can also say that when a wavelength of this much is incident onto the electron, it goes to the higher energy level also. It can also be used for excitations. Anyway, so that is the idea. Okay students, so let us solve some questions now based on these energies. So now, what is the energy of an electron in Li2 plus which has an angular momentum of h by pi? So they have given us the angular momentum as h by pi. So we know that in any hydrogen like species, the angular momentum of the electron can be understood as n times h by 2 pi. So the value that is given to us is h by pi. So from this we can easily understand that they are talking about an electron which corresponds to n is equal to 2 state. So the electron is in the second state or the first excited state, and now they are talking about that electron and they are asking us to find out what is the energy of such an electron in Li2 plus. So we already know the expression for energy of an electron in an nth orbit. So energy, the expression is minus 13.6 electron volts into z square by n square. So this is the expression which we have. So when I simplify this, I get minus 13.6 into z square. So Li2 plus, the atomic number for lithium is 3. So this becomes 3 square, which is 9 by n is 2, so 4. So we know the minus 13.6 by 4 is minus 3.4 into 9, and when we simplify this, you get minus 30.6 electron volts. So that would be the energy of an electron in this particular hydrogen like species and having this much momentum, angular momentum. Okay. Now let us move on to the next question. So here they are asking us to find the potential energy of an electron in the second excited state of He plus. So second excited state basically means n is equal to 3. So potential energy of an electron in the third orbit of He plus. So first let us find the total energy, then we can find out the potential energy. The expression for total energy of an electron is basically minus 13.6 into z square by n square. So when I substitute the values, I get minus 13.6 into z is 2, so 2 square by 3 square. And so that is the expression for total energy, but they are asking us to calculate potential energy. So how do we find the potential energy of an electron? So we already know that potential energy is nothing but twice of total energy. So we can directly say that the potential energy is twice of this value. So that is minus 13.6 into, this is 4 into 2 gives you 8 by 9. So you can just simplify that. So that would be the answer. So another question, it is given an electron is in the ground state of hydrogen and it is given an energy of 12.1 electron volts. Its initial time period was T1, which means in its ground state the time period of revolution was T1, and after getting excited its time period is T2. They are asking us to find the value of T1 by T2. So I have already told you earlier, by looking at 12.1 you should immediately get the idea of which transition it corresponds to. An electron in ground state when supplied with 12.1 electron volts of energy gets excited to third state. So here the transition is from 1 to 3. So this is the initial state and this is the final state. So now basically they are asking us to find out what is the ratio of time period in the first orbit to the time period of electron in the third orbit. So we already know the relation between the time period and n. So even if you are not aware of the relation between t and n, I hope you remember this relation which we discussed between t and the radius. So we know t square is proportional to r cube. So you can use this also. So it basically means that t square is proportional to r. R, we all know that r is proportional to n square. So n square power 3. So which means t square or t is proportional to n cube. So this is the relation. So using this you can directly substitute the values. We can directly say that, so time period of electron in the first orbit divided by time period of electron in the third orbit will be equal to 1 by 3 whole cube. So the value of this would be equal to 1 by 27. So that would be the answer. So it is given that a photon is released during the de-excitation from 6 to 3 in Li2 plus, and that photon is absorbed by an electron in the ground state of hydrogen. They are asking us to find the angular momentum of the electron in the excited state of hydrogen. So if I consider Li plus 2, so in Li plus 2 there is a transition corresponding to 6 to 3, and whenever de-excitation occurs a photon is released. So there is one photon which is released from this de-excitation, and this photon has struck a hydrogen, an electron in hydrogen which is in the ground state. So now we will have to find out, by absorbing this photon, this electron in the ground state reaches which state, and once we are able to find out to which state it gets excited to, we can easily answer what the angular momentum of the electron would be in that excited state. So now let us first understand this expression. Let us find out what is the energy corresponding to this de-excitation. We can directly write that expression as 13.6 electron volts. So the expression is into z square by n square. So the difference in energy would be 1 by 9 minus 1 by 36 into, because that is lithium which has an atomic number of 3, so 3 square. 13.6 into z square into 1 by n1 square minus 1 by n2 square. So that is the expression which we get, and when I simplify this, this is also 9. So I can understand this as 13.6 electron volts into 1 by 1 minus 1 by 4 is what I would be getting. You can also understand that there is a 1 square over here. So I am just writing it this way so that you can actually see a correlation with hydrogen transition. So this basically represents, can you guess, this is 1 by 1 minus 1 by 4, and here you have 1 square. So can I say that this transition in Li plus 2 has the same energy difference as which transition in hydrogen? It has the same energy as, this is 1 square and this is 2 square. So we can say that this transition has the same energy as 1 to 2 transition in hydrogen. So 6 to 3 transition in Li2 plus has the same difference as 1 to 2 transition in hydrogen. So, it means that the electron has excited to the second state, and they are basically asking us to find the angular momentum of the electron in the second state. N is equal to 2 state. So, we can easily say that the angular momentum L is equal to n times h by 2 pi, and the value of n in this case is 2. So, this becomes h by pi. So, that would be the answer.